Good afternoon. Can you hear me and see my screen?
Yes.
Thank you. So just to recap where we were the last time, we discussed, so just let me maybe, we discussed the spectral norm, which we defined to be maximum square root of lambda, where lambda is an eigenvalue of A Hermitian A. And the spectral radius which we define to be rho of A is the maximum magnitude eigenvalue where lambda is an eigenvalue of A. Okay. We also saw that rho of A is less than or equal to the norm of A for any matrix norm. And if there is a norm such that norm of A is less than 1, then limit k tending to infinity, A power k is equal to 0, and such matrices were called convergent. And we saw that A is convergent if and only if rho of A is less than 1. And further, this rho of A, it's a lower bound on any norm of A, and it's also the greatest lower bound in the sense that given A in C to the n cross n and epsilon greater than 0, there exists a norm such that rho of A, or the norm of A, is between rho of A and rho of A plus epsilon. So in other words, I can find a norm such that the norm of A will be as close to rho of A as I wish. And further, the spectral radius can be used to bound the entries of A power k. So if A is in C to the n cross n and epsilon is greater than 0, there exists a constant C such that A power k ij is less than or equal to C times rho of A plus epsilon power k. And this is true for every k, I, and j. We also saw that A is invertible if there is or there exists a matrix norm such that norm of I minus A is less than 1. And if so, A inverse is equal to sigma k equal to 0 to infinity I minus A power k. So about this, I made a note the last class that A may be invertible if, say, row of I minus A is greater than 1, i.e. norm I minus A is greater than 1 for all matrix norms. Okay, so I just want to maybe make this point a little more clear, because I think the last time it was not entirely clear the way I said it. So basic logic says that if you have a statement A, and if we say A implies B, then it means, so if A implies B, then not B, which I'll write as B complement, implies A complement, but B does not imply A. Okay, this is the basic rules of logic. Now, in this case, what is A? A is the statement that there is a norm such that norm of I minus A is less than 1. The statement B is that A is invertible. Okay, and so now let's look at these statements and see what they mean. So what the result says is that A is invertible if there is a matrix norm such that norm of I minus A is less than 1. So that means if it is true that there is a matrix norm such that I minus A less than 1, then A is invertible. That implies that A will be invertible. So this A, norm of I minus A less than 1, this A implies B. So this is true for these two statements as I have written here. Now what is B complement here? B complement is that A is singular. Okay, so B complement, so if A is singular, it means the complement of A. What is A complement? A is the statement that there is a norm such that norm of I minus A is less than 1. The opposite of this statement is that norm of I minus A, there is no norm such that I minus A norm is less than 1, which means I minus A is greater than or equal to 1 for all matrix norms, or for any, let's say. Okay, so it means, so B complement implies A complement is the statement that if A is a singular matrix, then if you compute norm of I minus A, you will always get a number that's greater than 1, no matter which norm you pick. Okay, and what is B does not imply A here? B is the statement that A is invertible. It does not imply that there must be a norm such that norm of I minus A is less than 1. So B does not imply A. In other words, it is possible that there is a norm such that I minus A is greater than 1, but A is invertible. Okay. So the invertibility of A does not imply the existence of a norm such that I minus A norm is less than 1. But if this condition is satisfied, there is a norm such that I minus A is less than 1, then A will be invertible. I hope that is a little more clear than how we discussed it the last time. And at the end of the previous class, we saw the Banach lemma. Which said that if B is an n cross n matrix and this is an operator norm, then if norm of B is less than 1, then I plus B is invertible, and 1 plus norm of B inverse is less than or equal to norm of I plus B inverse is less than or equal to 1 minus norm of B inverse. Okay. So one thing I'll say is that a form like I plus B arises very frequently in many problems. And I'll show you an example today of where you'll end up with a form that looks like I plus B. And then what happens is you know something about this matrix B. In particular, if you know some norm of that matrix, this allows you to bound the norm of I plus B inverse in terms of how big the norm of B is. So that's why these kind of results are useful. Okay, now so this is basically about the recap of what we did the last time. Okay, so yeah.
Sir, could you explain the difference between any and every?
In this context,
Yes, yes.
there is no difference. Okay. So the thing is that now, yeah, so in this kind of contexts, there is no difference between any and every. Now, where it will make a difference is, for example, if A were a random matrix, okay, then you would be associating a probability with which this event will happen. You will say I minus A is greater than or equal to 1 with probability greater than 1 minus epsilon or something like that. In those kind of contexts, there is a difference between saying any and every. What you mean by any is that you will fix a norm first, and then you will take different instantiations of this matrix A, and you will try to see what is the probability that, or what is the percentage number of cases where I minus A norm is greater than or equal to 1. And that is the probability that you're bounding when you say for any matrix norm. But when you say for every matrix norm, what you will do is you will pick an instantiation of A and you will ask what is the probability that all matrix norms of I minus A are greater than 1, greater than or equal to 1. And a matrix fails this if there is a norm for which norm of I minus A is less than 1. And then you ask, if I take different instantiations of this matrix A, what is the probability of success of this event? This is well beyond what we want to cover in this course, but I mention this only to tell you that in this context, any and every are actually this one and the same because we have fixed the matrix A. We are only looking at whether this norm is greater than or equal to 1 for this given single matrix A. But when we start talking about random matrices, there is a difference between any and every.
Thank you, sir.
Welcome. Okay, so there's just one or two more results I want to mention. So one use of this result, which says that if there is a norm such that the norm of I minus A is less than 1, then the matrix A is invertible, is in showing the following corollary, which is called the Levy-Desplanques theorem. Okay, so which says, incidentally, is there anybody in the class who can speak French?
Yes, sir.
So you would know that this word here, this name, we pronounce it approximately like Desplanques, but
Diplom.
for the English, yeah, exactly. For the English speaking world, it seems like there are so many extra letters here, and you don't pronounce any of them. You certainly don't say Desplanques. But the interesting thing is, from the French point of view, DES is actually pronounced de, and QUES is actually pronounced K. And so this is just Desplanques, and that is the correct. I mean, you are as far from a for the French, they're actually exactly reading it as it is written. They're not ignoring any letters. Um, but for us, it appears like for those who are not familiar with French, it appears like there are so many extra letters and that are not pronounced. And this is true of a lot of French words. When you try to read them from an English point of view, you feel like there are so many extra letters that are not being pronounced. So yeah. So anyway, what A n cross n, and suppose mod AII is greater than sigma j equal to 1 to n, j not equal to I, mod Aij for I equal to 1 to up to n. What does this mean? It means that if I take the diagonal entry and I compare that with the sum of the magnitudes of all other entries in the same row but all across all other columns, then the diagonal entries magnitude is strictly bigger than the sum of all other entries in magnitude in the same row. And such matrices are called diagonally dominant matrices. And they are very important from a matrix theory point of view. We are going to see a lot more about such matrices. Again, with because in many signal processing manipulations, you end up with matrices which are diagonally dominant. So, for example, if you think about computing the covariance matrix of a random weight vector, the diagonal elements of the covariance matrix represent the individual variances of these random variables, while the off-diagonal entries represent the cross covariances between these random variables. And typically the cross covariances are small compared to the variances of the random variable. And so under some assumptions, of course, about the underlying set of random variables that you're looking at, these cross covariances could be small enough that the matrix satisfies a property like this. And so then everything we say about diagonally dominant matrices apply to covariance matrices of such kind of a dominant, then A is invertible. So this is interesting because what it says is that so if I take a 2 cross 2 example, let's say, and let's say just for fun I write 2 and then 7 here. Now I'm allowed to write, for variety I'll say -7 here. I'm allowed to write any number here and any number here, with the only requirement that the magnitude of this number, so I call it x, the magnitude of x must be smaller than 2, and I'll call this y, then magnitude of y must be smaller than 7. You can try your luck with putting down any number here. It could even be a complex number here, this will always be invertible. Okay, that's just to give you an idea of what this theorem is saying. So let's show this. So AII is strictly bigger than the sum of all the off-diagonal terms in the same row, and these are all non-negative because it's the magnitude of some number. So what this means is that this itself is greater than or equal to 0, which means AII is strictly bigger than 0. By the hypothesis. That means that all the diagonal entries of this matrix are strictly positive. So if I take the matrix D defined to be diag of A11 through ANN, this will be invertible. It's a diagonal matrix with strictly positive entries, strictly positive magnitude entries. In fact, the inverse of this is just A11 inverse, A22 inverse up to ANN inverse. So then, if I consider the matrix B equal to I minus D inverse A, what this will do is, this is a diagonal matrix which is operating on A. So what happens to the diagonal entries? The diagonal entries get scaled. The first diagonal entry will get scaled by A11 inverse. The second diagonal entry of this matrix will get scaled by A22 inverse, and so on. And so when I consider D inverse A, all its diagonal entries will be equal to 1. And so this matrix B will have this identity matrix of course has ones on the diagonal. So when I subtract these out, the 1 and 1 will cancel, and this matrix will has zeros on the diagonal. And for the off diagonal entries, it will have minus Aij over Aii as ij the entry, I not equal to j. Okay, this is just the fact that when I pre-multiply by a diagonal matrix, every row of A gets scaled by the corresponding entry of D inverted. Now, consider of course, the off-diagonal terms in the identity is 0, so it becomes 0 minus Aij divided by Aii, which is minus Aij over Aii. Okay, now let's consider specifically the max row sum norm. So you can already probably start seeing how this proof works out. I'm going to add up the entries across each row in magnitude, and then I'll take the maximum value. Now, since sigma j equal to 1 to n, j not equal to I, mod aij over mod aii is less than 1 for every I. Okay, and now I'm doing j not equal to I, but the corresponding I comma ith entry of B is just 0. So when I compute the row sum norm, each of them will be some number like this, and it's less than 1. And why is this less than 1? It's because of this condition here. I'm just taking mod aii to the other side. So this summation, the summation of j equal to 1 to n aij over aii for is going to be less than 1. And this is true for every I, which implies that the norm of B infinity which is just the max of all these guys, is also going to be less than 1. So B infinity is less than 1. That is this, the L infinity norm of this is less than 1. So there is a norm such that the norm of I minus D inverse A is less than 1, which then means that I minus B, which is equal to D inverse A, is invertible. But D is a non-singular matrix, so which implies that A is invertible. Okay. So basically, all diagonal dominant matrices are invertible.
Sir, can you please repeat the point why A is invertible?
See, this
From
is a
G.
product of two matrices. Okay, a product of two matrices will be invertible only if both the matrices are invertible. You've seen that already in previous classes. Also, you've done homework problems on it. That if you write a matrix as a product of two matrices, and if that matrix is invertible, then each of the constituent matrices must be invertible.
Okay, sir.
Okay, so now there are just a couple of more points before I close out this particular line of discussion, which has to do with, remember we talked about equivalence of vector norms. There is a similar thing we can say about equivalence of matrix norms.
Sir, so the converse is valid or not in above theorem?
Which theorem?
Do all invertible matrices need to be diagonally dominant?
What do you think? Is this matrix invertible?
Yes.
Of course, right? Its
Oh,
determinant
yes.
is minus
Yes.
1, right?
Yes.
In
Yes,
fact,
sir.
its inverse is itself, right? You multiply this matrix by itself, you will get the identity matrix.
Yes, sir, I got it.
It's not diagonally dominant. So again, it's a good point because all these theorems are usually very carefully stated. If there's any error if there's anything weird or inconsistent in the statement, that's purely my mistake in writing the theorem down. The textbook actually is very, very good. The theorems are all extremely carefully stated. And so when it says if, so what it's saying is if a matrix is diagonally dominant, it will be invertible. It does not mean that every invertible matrix will be diagonally dominant. The converse is not true.
Hello.
Yes, please.
That matrix which you have represented above, that is 0, 1, 1, 0. So is there any name for
Yes.
it? Anti-diagonal? No. Sorry.
It's a
This one, yeah.
permutation matrix.
Okay, okay.
See, if I multiply xy,
Okay.
what I'll get is yx.
Okay.
Okay, it permutes the entries of the vector. It's a
Okay.
permutation matrix, and permutation matrix have lots of very nice properties.
Okay.
Okay, and this is an example of a 2 cross 2 permutation matrix. Of course, the only other permutation matrix in the 2 cross 2 is the identity matrix, which doesn't do any permutation actually.
Okay.
It's the identity permutation because you have only two entries. You can either keep them where they are or you can exchange them. Nothing else you can do.
No, no. Here we have a diagonal, cross diagonal, where we have elements as 1, 1. Okay. So if you take determinant, it will be -1. So inverse exists.
Hmm.
Okay, okay. You're talking about the permutation. Yeah, I got it. Thank you.
Yeah. Okay, so the equivalence of matrix norms basically says that if you have two different norms, you can bound the norm of any matrix with respect to the first norm in terms of the norm of the matrix with respect to the second norm. And this is useful again because you may be interested in showing convergence of certain algorithms. And in these algorithms, you'll get a sequence of matrices. And once again, we've seen that if you are able to show that the sequence of norms of these matrices, if that converges, then the matrix itself will converge. And so we are often interested in showing that the sequence of norms of a matrix converges. But then for different problems, it may be more easy to take different types of norms and show that that particular norm converges. But that may not be the norm in which you are actually executing this optimization problem that you are interested in. Fortunately for us, these norms are all equivalent. So if one particular norm is converging, then every norm will converge. Maybe not to the same value, but to some other value. And so it is useful to have this kind of result on equivalence of matrix norms because it means we can use any norm that's convenient for us in trying to show convergence properties. So basically, given any two norms, two matrix norms, alpha and then there exists a least positive constant Cm of alpha beta such that the alpha norm of A is less than or equal to Cm of alpha beta times the beta norm of A for every A. In fact, Cm of alpha beta can be computed by solving Cm of alpha beta is equal to the maximum over all A not equal to 0 of norm A alpha divided by norm A beta. So you take this ratio and you find the biggest number it can take, then of course it must be true that norm A alpha is less than or equal to Cm of alpha beta times norm A beta for any other A, because that's like a suboptimal A that you're choosing which must satisfy this inequality. So if I in this, I just said alpha and beta, and there's no I can always just exchange alpha and beta, and the way to say that is that there exists this Cm of alpha beta, there exists similarly a Cm of beta alpha such that A beta is less than or equal to Cm of beta alpha times A alpha, and this Cm of beta alpha is computed as the maximum of norm A beta divided by norm A alpha. So that's a different, completely unrelated, sort of different optimization problem. So it's not, so basically in general, there is no relationship between Cm of alpha beta and Cm of beta alpha. But for induced norms, that is both alpha norm and beta norm must be an induced norm. They are equal. So this is actually theorem 5.6.18. Now the textbook has a lot of theorems. I obviously cannot cover all of them, but where appropriate, I'll indicate some theorems. Mainly, I'll focus on stating and proving theorems that we'll actually try and use later in the course. But this is just an interesting result that is there in the text that you can go take a look if you're interested. Okay, now there's just two more definitions. The first is the notion of a unitarily invariant norm. So we say that this norm is unitarily invariant. I'll write this in short here. This is the same as this statement here. If norm of A equals norm of UAV for every A belonging to C to the n cross n, and C to the n cross n. So one example is the spectral norm. Okay, is unitarily okay. This is a small exercise. Show this. Start from the definition, and you will be able to show that the norm of UAV spectral norm is equal to the spectral norm of A for any A and all possible unitary matrices. The second definition is so suppose is a matrix norm on C to the n cross n. Then so this is a new function I'm defining with an h on top, which is defined to be the norm of A Hermitian. Is also a matrix norm. Okay. Now this norm that I'm defining here need not be an induced norm. It's true for any norm, any matrix norm that I can define on C to the n. If I, instead of computing the norm of A, if I say the norm of A is this whatever norm I've defined operated on A Hermitian, that is also a matrix norm. It's actually straightforward to show this from the definition. So in particular, if you take the Frobenius norm, this is the square root of the sum of the squares of all entries in the matrix A. This is equal to, by definition, the A Hermitian Frobenius norm. So this is the Hermitian or the H norm of the Frobenius norm, which is the Frobenius norm of A Hermitian. Of course, a conjugate transpose doesn't change the sum of the squares of all of the magnitudes of all the entries in A. So this is exactly equal to A2. And similarly, we defined this with 2 bars A1 to be the sum of the magnitudes of all the entries of A. So similarly, if I define this H norm to be the 1 norm of A Hermitian, then again taking the conjugate transpose doesn't change the magnitudes of the entries in A. So this is also equal to A1. So this is what we call the L1 norm. And the spectral norm, so if I take the H of the spectral norm, I'll work with the square because that's easier. This is equal to, I have to compute, so when I take the H norm, I have to compute the spectral norm of A Hermitian instead of the spectral norm of A, and then I have to square it. Now the spectral norm of A, the spectral norm of a matrix is the square root of the largest eigenvalue of A Hermitian A. And so if I apply that to this, to A Hermitian, I get that this is equal to the square of this is going to be rho of the spectral radius of A Hermitian. And this is another result that you have to show in your homework, that rho of A Hermitian is the same as rho of A Hermitian A, which is equal to the spectral norm of A square. Okay, so I'm slipping in two different things here. One is that I'm showing that the spectral norm of A is invariant to doing this H operation. The H norm of the spectral norm is the spectral norm itself. And the second thing is I'm saying that the spectral radius has a nice relationship with the spectral norm in that the spectral norm squared, norm A2 squared, the spectral norm squared is exactly equal to the spectral radius of A Hermitian A. Okay, so that's the relationship between the spectral radius and the spectral norm. That's a relation between the spectral radius and the spectral norm. Okay, so this is homework. So you see that here when I take this H norm, it gives you the same norm. Here also when I took the H norm, it gives me the same Frobenius norm. And the H norm of the L1 norm is also equal to the L1 norm. Such norms for which H is the same as the norm itself are called self-adjoint norms. Okay, and by the way, note that if I compute the max column sum norm H, that is equal to the max column sum norm of A Hermitian, which by definition is the max row sum norm of A, and that is different from AL1, the max column sum norm of A. So this is not a self-adjoint norm. So max column sum norm and max row sum norm are not self-adjoint. Okay, so there's one very nice result that says that one, the spectral norm is the only matrix norm that is both induced and unitarily invariant. The second property is that the spectral norm is the only norm that is both induced and self-adjoint. Okay, the proof of this is in the text, but these are again two special properties of the spectral norm, which is one of the reasons why, multiplying by unitary matrices or taking the conjugate transpose operations are fundamental operations that arise in many signal processing and engineering applications, and that's why for many of these applications we are interested in working with the spectral norm because it's invariant to these two operations. It's a very special norm in that way. Okay, so we still have about 12 minutes in the class, but the next thing I want to talk about is about some uses of these norms. We've discussed several theorems, but now we can maybe talk about um, solving linear systems and how these norms help us, for example, in bounding the error in computing inverses or solving linear systems. Now, if I start on the next thing, I need about, let me see. Okay, so let's just maybe make a few remarks and see how far we can go. Inverses and solutions to linear systems. Okay, so basically if we are given a matrix A which is non-singular, we know that A inverse exists. But when we want to try to compute A inverse, then we may have to compute it on a finite precision arithmetic machine, or maybe we don't get to observe A. We only get to observe a noisy version of A. And then we compute the inverse on a noisy version of A. It turns out that under appropriate modeling, you can actually generally consider both of these as a system where, or a general simple mathematical model under which you can consider both these types of errors, is to consider that what you've inverted is some other matrix A plus E. So given A in C to the n cross n, non-singular. So pay attention to this. This is important. I'm starting out by assuming that the original matrix I wish to invert is actually non-singular, and that's why I'm brave enough to try to compute its inverse. And we wish to compute A inverse. So instead, we compute A plus E inverse, where E is an error matrix. So basically here E is small, such that A plus E is also invertible. So the error I've incurred will be this is like an error matrix, which is A inverse minus A plus E inverse, which I can write as, I'll pull out an A inverse out of this. So I'll write it as A inverse minus I plus A inverse E inverse times A inverse. Okay, I'm just using the fact that AB inverse is B inverse A inverse to write this.
Sir,
Now, yeah, go ahead.
so here we are trying to compute the inverse of a non-singular matrix. So this matrix E, is it deliberately added or is it observed? I mean,
So
is
I'm
it
not,
deliberately added to make it invertible?
no. A is non-singular to begin with.
Okay.
Okay, so I can freely write quantities like A inverse. Otherwise, this would be a meaningless thing to write if A could be singular. So A is invertible. A plus E is also invertible.
Okay.
It's just
Okay.
that I couldn't compute, or I didn't have A exactly in my hands. What I got to observe was A plus E, where E was a small perturbation on A,
Okay. Okay.
such that A plus E was also invertible. So I wanted A inverse, but I have A plus E inverse in my hand. The difference between these two is the error.
Yes.
Now, what we've seen is that if the spectral radius of A inverse E is less than 1, then we can write I plus A inverse E inverse is equal to, we can write this as a series, sigma k equal to 0 to infinity minus 1 power k A inverse E power k. So this is what we just recently we saw this result. Okay. So so we can write it like this. So now I'll substitute this in here, which means that A inverse minus I plus A inverse E inverse times A inverse is equal to A inverse minus sigma k equal to 0 to infinity minus 1 power k A inverse E power k times A inverse. Now if I take the k equal to 0 term, I'll get minus 1 power 0. This thing power 0 is the identity matrix times A inverse. So the first term here exactly cancels this A inverse. And so I'll be left with, this is equal to all the other terms, k equal to 1 to infinity. And I'll absorb this minus 1 into this and write it as minus 1 power k plus 1 times A inverse E power k times A inverse. Okay, so this is true if, so keep in mind my starting point is if rho of A inverse E is less than 1. Now suppose this is a matrix norm and A inverse E measured according to this Can you hear me?
Yes, sir.
Yes.
Yeah. So there was a power failure here, so I lost my internet for a few minutes, a few seconds. I had to connect to another network. Yeah, just to come back here. So now suppose there is a matrix norm such that the norm of A inverse E is also less than 1.
Screen
Then,
sharing is not there. Hello.
oh, I lost a lot of things. Okay, hold on.
Okay.
So suppose there is a norm like this such that norm of A inverse E is less than 1. Then,
yes, it's visible.
thank you. Then rho of A inverse E is also less than 1. And if I compute the norm of A inverse minus A plus E inverse, so that will be equal to the norm of this summation k equal to 1 to infinity minus 1 power k plus 1 A inverse E power k A inverse, which is less than or equal to, I'll take the norm inside and I'll apply the submultiplicativity, sigma k equal to 1 to infinity norm of A inverse E power k times norm of A inverse. Now this is not dependent on k, so it can come out of the summation, and norm of A inverse E is less than 1, so this is summable, and so I can write this to be equal to norm of A inverse E divided by 1 minus norm of A inverse E times norm of A inverse. So we now know, thus we know that the relative error, if I define it to be norm of A inverse minus A plus E inverse divided by the norm of the guy I wanted to compute. So this is the relative error in computing A inverse. This can be upper bounded by norm of A inverse E divided by 1 minus norm of A inverse E. If norm of A inverse E is less than 1. That was the assumption we made. So we see that norms are useful to help us bound the relative error in computing things like A inverse. There are many more uses which we will see in the next class, also with respect to solving of linear equations. But we'll stop here for today, and we'll continue on Monday. Thank you.
Sir?